Welcome to The Explainer. Today we're looking at a massive, absolute, paradigm-shifting leap in science. For decades now, the promise of quantum technology, unhackable networks, infinitely powerful computers, revolutionary sensors, it's all been dangled right in front of us. But it's been trapped, literally trapped behind this invisible, freezing barrier. Well, today we're finally breaking out of that freezing past. We are entering the room temperature quantum revolution.
To really understand this breakthrough, we first have to understand the bottleneck, right? So why is quantum tech currently frozen in a laboratory? Because despite all the hype you hear, almost all known quantum materials only exhibit those mind-bending properties when cooled to temperatures hovering right near absolute zero. We are talking colder than deep space. It's staggering to think about. But why? Well, because at everyday room temperatures, heat creates constant atomic vibrations, and these vibrations act like noise, completely overwhelming and destroying the incredibly fragile quantum state scientists are trying to harness.
Let's dive into this contrast for a second. The cryogenic era is entirely defined by these bulky, multi-million-dollar refrigeration systems. Systems that, by the way, come with a monthly utility bill you probably don't even want to think about. That limits quantum tech to highly controlled, incredibly expensive laboratories. But the room temperature era? This is where quantum mechanics actually meets everyday conditions. It means compact designs and highly practical, real-world applications. The lingering question has always been, how on earth do we cross that gap?
Section 1. Forging a gold metacrystal. Building the solution. Instead of wandering around searching nature for some magical material that works at room temperature, a team of physicists at LSU just decided to build one from the ground up.
And here is exactly how they forged this solution. The team started by depositing an ultra-thin film of gold onto a totally standard glass chip. Then, using highly focused ion beams, they carved hundreds of microscopic slits right into the gold. Each of these tiny slits acts as an artificial atom, or what physicists like to call a meta-atom. By arranging them with extreme precision, they engineered a crystal thinner than a human hair that simply has no counterpart in the natural world. And step 3 is the absolute kicker here. They tested it using a laser-based optical setup entirely at room temperature. No freezing required whatsoever. They created something so entirely unique, they actually had to invent a new name for it. A quantum statistical plasmonic metacrystal. Now, I know that sounds incredibly intimidating, but underneath all that heavy scientific jargon, it's basically just a physical filter. It's a smart sieve for light. By precisely engineering those artificial meta-atoms, this material systematically dictates which quantum states are allowed to pass through it. It effectively sorts them automatically, completely removing the need to freeze the environment to keep them stable. And this wasn't just some theoretical win. It was a massive experimental triumph. Chenglong Yu, a key researcher on the project, noted the sheer thrill of building a material that nature just doesn't provide on its own. They envisioned a physical geometry that could control quantum states, built it, and then got to watch it work flawlessly. It's a true testament to the power of structural engineering over brute force cooling.
Section 2. Sorting light at room temp, the mechanics. So how exactly does this physical filter actually work?
First, we really need to grasp what we're trying to protect here: quantum coherence. This is a super delicate state where the shared behaviors and subtle statistical differences of interacting particles, like photons of light, are maintained. Because remember, not all light behaves the same at the quantum level. To tell those states apart and actually keep them intact, scientists usually need highly sophisticated instruments, cryogenic detectors, and literally millions of individual measurements. It is incredibly exhausting, delicate work. But the metacrystal, it changes the game entirely. The crucial point is that it does all that heavy lifting automatically. As light hits the gold surface, the physical geometry of those carved meta-atoms immediately interacts with the light. It recognizes those subtle quantum distinctions and directs specific states along different pathways, straight through the crystal. It achieves what researchers call robust transport, meaning it moves quantum information from point A to point B without losing its defining characteristics to heat and vibration. And this breakthrough establishes a totally new engineering framework. The researchers discovered that this crystal naturally forms quantum statistical bands, which is pretty similar to how semiconductors conduct electricity. But because they built it, they can program it. By simply changing the arrangement of those tiny slits, scientists can dictate exactly which quantum states pass through unaltered. So this isn't just a cool one-off experiment, it's a blueprint. We can now intentionally design materials to guide quantum states exactly where we want them to go.
Section 3. The 2D topological insulator. A global paradigm shift. Because the most thrilling part, LSU isn't alone in this race.
Over in Finland, teams from the University of Jyväskylä and Aalto University achieved another major milestone. They brought a decade-old theoretical quantum material into reality. By growing just 2 atomically thin layers of tin telluride on top of a specific substrate, they created a 2D topological crystalline insulator. Basically, the substrate physically compresses the tin telluride, and that physical compression acts as a substitute for freezing temperatures. It stabilizes special conducting pathways along the edges of the material, pathways that are predicted to remain completely stable even at room temperature.
And this brilliantly illustrates the wider revolution happening in physics right now. On one hand, you have LSU carving microslits to sort light. On the other, Finland is using mechanical strain to stabilize electron pathways. 2 completely different materials, 2 completely different structural techniques, but both are solving the exact same cryogenic problem. We are quite literally replacing the brute force of freezing temperatures with the elegant precision of physical geometry.
Section 4. Unlocking future quantum tech, the real-world impact. So, what happens when we finally pull quantum technology out of the freezer and put it into the real world?
Well, the applications start right now, with technologies we already use every day. The LSU team's immediate next step is to integrate their metacrystal into solar cells. In normal solar panels, a whole lot of sunlight just gets trapped in the material, vibrating and turning into useless heat instead of electricity. But if this metacrystal can sort light and guide it along robust, stable pathways, it could prevent that energy loss, drastically maximizing the electrical output of our renewable energy grids. That's a huge deal.
And beyond solar, this is the master key for the technologies of tomorrow. By mastering room temperature quantum stability, we're looking at quantum computers that can sit on a desk instead of inside a warehouse-sized refrigerator. We're looking at unhackable communication networks that actually operate in everyday environments and highly sensitive nanoscale sensors for medicine and defense. We are taking the absolute most advanced physics in the universe and embedding it directly into our daily lives.
We have spent decades trying to fight nature by freezing it. Now, by fundamentally engineering the structure of materials at the atomic level, we've bypassed the barrier entirely. The cryogenic era is ending, right before our eyes. The room temperature quantum era has officially begun. So I'll leave you with this. With the temperature barrier finally broken, what new quantum reality will we build next? Thank you so much for joining me for this explainer. I really hope this sparks your curiosity about the incredible future being engineered right now.